Hello everyone, I hope you are doing great. In this tutorial video, I want to talk about light emitting diode simulation with COMSOL Multiphysics. At first, I would be happy if you like this video, subscribe to my channel, share your comments, and introduce my channel to your friends. Let us start. As you can see, I have to simulate the related structure that consists of two contact, P contact and N contact in different side of the LED, and we use the 2D axisymmetric geometry to have this surface. It means the circle as 2D or 3D shape, as you can see. And also before the starting, I bring a simple schematic for the light emitting diode, as maybe you see in the industrial and in the chips of the electronic devices. You can see this simple structure of LED that consists the epoxy lens, semiconductor die here, post-lit frame, anode and cathode, which consists and from the mill steel lit frame, also anvil lit frame, reflective cavity here, and wire bond. The semiconductor die, that it means this structure which is consist different semiconductors. Here we have gallium arsenide for the simplest model, and although you can use the perovskite, you can use the silicon and other LED material. Here we have P layer, active layer, and N layer, that the same as solar cell. We have a contact that we can apply the positive and negative terminal biases to see the illumination from the active layer. That means the LED is turned on. And here we have a simplest schematic, and also here we can see the charge carrier recombination. Here we need the light recombination. The radiative recombination is important to achieve a good LED with high efficiency. Okay. Before starting the simulation, I want to talk about deeply of LED, and in this model we want to simulate LED that emits in the infrared part of the electromagnetic spectrum. In the structure is made of a single p-n junction formed by a layer of p-type doping near the top surface of an otherwise n-type wafer. In this kind of device, geometry is simple and cheap to produce, and similar LEDs that are found in many household applications, for example IR emitters in TV remote control and other controls for the electronic device. In this model, the optical transition feature will be used to calculate the electroluminescence of the device, and also the electronic properties are computed, and the efficiency of the light production is assessed. Also, by visualizing the spatial distribution of the radiative recombination, we can make a possible design for suggesting the maximum total efficiency of output light. Also, the infrared LEDs are widely used in many optoelectronic applications, but the most familiar in a household setting is for use in remote controls. Also, more efficient light production can be achieved using complicated device structures. Simple PN junctions are still used for many IR emitters due to their low cost and case of manufacture. In this model, we want to simulate a simple PN junction infrared LED. The device geometry is a cylindrical symmetry, which enables a 3D visualization of the results in a shorter time of the computation. This model shows an example to how to use the semiconductor initialization study to create a refined mesh in cylindrical geometry, and this is useful because we can automatically refine the mesh around the PN junction. And in the second study, we use a stationary study that we sweep the applied bias voltage of the device to see the current voltage curve and also optical emission characteristics of the LED. Okay. Here we have a device that is made of 60 micrometer diameter circular chip of gallium arsenide, and due to crystalline nature of the semiconductor material, actual LED chips are likely to be fabricated using rectangular chips. Only the circular active region formed by the P and N type doping is included in this simulation. This is in order to allow cylindrical symmetry, which considerably reduces computation time, because the R0 axis is an axis of symmetry. The device geometry is represented by a 30 micrometer wide rectangle with a thickness of 10 micrometer. The bottom 7.5 micrometer of the device are N-doped, and the top 2.5 micrometer are P-type. And the rectangular trench has been etched down to the N-type layer at the right hand side of the domain to allow an electrical contact to be deposited onto the N-type side of the PN junction, that creating a ring of metal around the edge of the device. And then the P-type contact is deposited directly on the top of surface in the center of this chip. And also we use optical transition feature that is allow electroluminescence to be calculated. This is achieved by clearing the simulated emission checkbox within the feature such that only the spontaneous emission will be calculated. In the absence of any optical excitement from an incident electromagnetic field, the spontaneous emission will be the electroluminescence due to the carrier dynamics of the injected current. An Auger combination feature has been added to include a non-radiative recombination mechanism. This is only one possible non-radiative recombination mechanism. In reality, a variety of other processes may be present, such as lattice impurity scattering and phonon interaction. However, for the purpose of this demonstration model, origin recombination is sufficient to capture the important behavior that the efficiency of the radiative emission drastically reduces with increased current density. Although this model used two studies, the first is semiconductor initialization, and that is used to automatically refine the mesh around the gradient of dopant concentration. This is useful because the refined mesh is denser around the p-n junction, which is where a smaller resolution is required. The second study sweeps the voltage bias across the device from 0 volt to 1.5 volt. The current voltage is plotted to show that the device is indeed a diode, and the emission rate throughout the device is calculated. Okay, let us start it. At first, I opened the COMSOL Multiphysics. I used the version of 6.2. Okay. In the section of new, I use the model wizard. In model wizard, I choose 2D axisymmetric. And then from semiconductor, I choose semiconductor semi. Then click add. And I add the semiconductor. Then I go to click the study. From the study, I use the semiconductor initialization. I double click on it. And this model will appear here. Okay. Now I go to the parameter section and I write these variables. I mean parameter Vn 0 volt, that is mean voltage of n type, and Vp is equal to 1.5 volt p-type voltage, okay, and the other parameter is W down, that is equal to 25 micrometer. Domain width and H down it's equal to 10 micrometer, which means the domain height and W con n W dom divided by 5. W con, which means width of n contact, and H con n, that is equal to H dom divided by 5. W con P is equal to W dom minus divided by 10, and HP, which means the height of surface of p-type layer, which is equal to H dom divided by 4, and R fill, it is equal to 0.25 micrometer, that is equal to field radius that we talk about. Okay. I go to geometry 1. You can see here. In the geometry, I go to the setting windows, and in the unit section I choose the length unit to micrometer, and I click right on it, and I choose a rectangle. In rectangle 1, in the width, I type the W dom, and in height, I write the H dom. Okay. And I build it. And I click right on the geometry. I choose another rectangle, and in the width I type the W con n, and in height I type the H con n, and in the R position I write the W dom, and I build selected, and you can see this figure. Okay. I choose Boolean and partition. In Boolean and partition, I choose a union, and I press the control. I choose Control A here, and I untick the keep interior boundaries, and I build all objects. And you can see the uniform shape of the rectangle. Okay, I add the polygon. I go to geometry. I go to more primitives, and I go to polygon. In polygon, I choose a table for data source. I choose 0 for first R, and the Z I choose HDOM, and for another one I choose WCON P and HDOM. Okay, then I will select it, and you can see this line is created, which means the contact of P. Okay, I choose a fillet. Let me click right on it. I choose a fillet. In the fillet, I choose I Control A, and also I could write the uni 1, the section 4. Maybe I can Control A. I just choose F. I can remove them. I just want to use this, and I click right on just the section, the point 4, and the radius I choose R fill. That we define it in the parameters. Okay, we can build all objects. I choose form union, and I left it as automatic repair tolerance. Okay. Now it is important thing to add the material, and in the material I click right on it. I can add blank material and define it, the related properties of material, for example perovskite, for example gallium arsenide, silicon, CIGS, and other semiconductor material. And here I browse material from, or I add material from library. Just I search gallium arsenide, and search it. In the semiconductor, part, I choose the gallium arsenide. Okay, as you can see, we have the properties of the gallium arsenide, and if you change these properties, it means you have another material. And okay, I go to semiconductor, I click right on it, and I choose the group by space dimension. Here for the carrier statistics, I choose Fermi-Dirac statistics for the carriers. In the semiconductor material, I choose the temperature and also the other properties are taken from the material. For example, relative permittivity, band gap, affinity, effective density of states, electron mobilities, and for initial values, I check the automatic section. You can also use the other options, but I leave it as automatic. I click right on the semiconductor. I go to domain and I choose the doping. I choose a geometric doping model. Okay. I can write it as the P doping and I select the related geometry that you can see the geometry 1. In the distribution part of the density, I choose a different part. Let me check this value. And also I can add the domains. Excuse me, for P doping, it's better use a box model. I remove it and let me delete this file. I choose analytic doping model for P type. I click on the related geometry. I choose a box, and then I go to acceptor doping density, and I change it to 1E18, 1 per cubic centimeter. And the base, I choose a corner base, and for position I choose 0 and H dom minus HP, and W is equal to W dom, and height is equal to HP. The profile, I choose a Gaussian profile, and also for junction depths I choose a decay lens, and for decay lens I choose a 2 micrometer. Okay. Another time I right click on domains, I go to doping and I choose analytic doping model. Here for analytic doping model 2, I choose n-type. I click on the related geometry distribution. I choose a box. In the box I write the 1E18 as a density, and here we have acceptor doping, but here we must choose a donor doping, and we must recheck the data 1E18. I choose a corner, and the base position is I choose 0 0, and the width I choose W dom plus W con n, and height it's equal to H dom minus HP, and the profile I choose a Gaussian profile, and a specified profile length it's decay length, and I choose a 2 micrometer. Okay, and for considering the luminescence effect and radiation, I choose optical transition, and in optical transition I add this geometry. I just take the spontaneous emission because we have LED. If we could, if we want to simulate the laser, we must take the stimulated absorption and emission, but here we have LED that is work based on the spontaneous emission, and we just take this option. And the matrix element for spontaneous lifetime I choose 2 nanosecond, and other property I just leave these properties as the properties of the default. Also I want to add the Auger recombination as I talk about it. Auger recombination, and the properties of Auger recombination factor for electron and holes are readable in the material property. Okay. Now we must to add some properties of contact. I mean the p-type and n-type contact. Let me add the contact of p. I add the metal contact. For p contact I add the top of this line metal contact, or p. Let me p contact, and I can add the, and also for the voltage I choose VP for the voltage of this contact, and I choose the ideal ohmic, as a contact type. I add another contact, that means N contact, and I consider here, and also the voltage I choose Vn. Okay, terminal 2, and I choose as a default ideal ohmic. It depends on your contact. You can add the Schottky contact by ideal Schottky, and you need the work function or barrier height. It depends on your structure, but here for simplicity we add the ideal ohmic. Okay, here I also add the definition. In the definition part I add the non-local coupling integral or integration. I add all of the geometry. In domain I choose integration for in the order of 4 in a spatial of R, phi, and Z, and I take the compute integral in resolve geometry. Okay, because we want to use this function in the results, I add it before the computation. Now I want to add the mesh. Let me check the mesh. I just right click on the mesh and let me build out. If we choose a physics control, we can see this mesh. And we can choose normal or finer. It depends on your geometry. Here I choose normal, but maybe finer it's better because the good quality of the resolution. And but for the simplicity I choose a normal, and you can see the mesh. I add another mesh also. Let me add the mesh from the top bar. I choose another mesh. Okay, I rename it as adapted mesh. Which will be from the maybe study, and we could add let me check the meshes. Excuse me, for adapted mesh we can just add another mesh. Let me check the We can add for example, another mesh and add it as the study control, because we don't have any adapting mesh here. Okay, I choose it as adapted mesh. Okay, here I go to study 1 and also here I can add the geometry and also the mesh. I could add the mesh from the mesh 2 or mesh 1. And let me add the mesh. Also we can add the mesh 1. It depends on it is not important. I choose mesh 1. From adaptation and error estimates I choose this one, and I choose a functional, and I choose a manual functional. I write this code, root.comp 1 dot semi dot int let me show you. Semi dot, we just write the root.comp1 dot semi dot int underline adapt sqrt d root dot root dot comp one dot semi dot m f semicolon root dot r cubic excuse me it is squared plus d root dot comp 1 dot semi dot m underline F root dot Z squared maybe one parenthesis is okay. Must recheck this code. Control A, Control X. I can write it on the Word. Let me check the final code in the Word. root.comp1.semi.int adapt parenthesis sqrt d root.comp1 semi.m f root.r 2 plus d root.comp1 semi.m f root.z 2 this is right here. V. Okay, now the code is okay, and just keep continue. I choose error estimates, and also I save the solution, and I choose a rebuild mesh for adaptation method. It means the mesh will rebuild, and the geometry I choose entire. The maximum number of adaptation I choose 1, and I add another study from the study top bar. I add a study. I choose a stationary. I rename it as voltage sweep. Voltage sweep. Okay. And in stationary, I choose a physics control mesh, and in a study extension I add the voltage, VP voltage, and the range. I choose the logarithm range for that. Excuse me for that. Must be lowercase word. Log range one 25 to 3.5. look range 3.6 0.1 4.5. okay, and it seems we have now it's okay. And let me compute the study first. Okay, after study first, you can see the new mesh was generated, which means the adapted mesh, and we can choose the adapted mesh for the second study, which means in mesh selection I can choose a level 1 adapted mesh. That we don't need this mesh because just I want to show you that this mesh will create. And you can see this adapted mesh is the good and best mesh for our simulation, and we can choose the adapted mesh for the second study. Okay, and now we can compute it to see what will the result. Okay, it means we don't define the some properties, and let me define these properties. The Auger recombination factor Cn is equal to 1e minus 31 centimeter to the power of 6 divided by second, and also the same for the whole Auger recombination factor 1e minus 31. Yes, exactly. And I recompute it again to see what the result will be. Okay, now we can see the convergence plot here. And you can see the convergence plot is very good. The error bar is lower than 1e minus 10, and it is good news for our simulations. Okay, you can see the basic default of the simulation result. For example, hole concentration, electron concentration, and net dopant concentration, and other property, as you can see. Also the 3D models of the electric potential, and the important parameters and the result, it's a current voltage, emission rate that we want to plot it. Let me add the 1D plot group. In the 1D plot group, I can add the global. In the global, I just write the contact properties for the terminal, for example, current for terminal 1, and also I add data set from voltage sweep. I can add the parameter value or expression for adding the voltages, but the parameter value is okay, and I can plot it, and you can see the terminal current as a amp, or you can convert it to milliamp. That is from 0 to 90 milliamps, and you can talk about it, think about it, about what will the results, what the meaning of this result. For example, here you can see after voltage of 1.2, the diode is turned on. This is a shape of diode current, and from 1.2 the diode is turned on, and it means the LED is on, and you can extract the light emission from that. Okay. Other important properties is emission rate. Let me simulate that. Just I go to the result, I add 2D. In the 2D I add the surface, and in the surface I can search it, for example in semiconductor, or maybe in extra dimension for geometry, for mesh. We can add some special operator for doing some measurements. Okay, in optical properties, let me check the extra dimension. In extra dimension you can see total emitted power per unit volume, per unit energy. Let me plot it. It must be defined. Let me check it. We must add the domain related to these properties. Just we can search another. We just wanted to find the emission rate. Just let me check the transport or optical properties. Here we can see many data, but just let me for example, let me check the semi.ot1 dot r spontaneous. Okay, and we can see, let me check it for the voltage of 1.2. You can see the spontaneous emission recombination rate, that is the LED in this voltage, it means the LED is on, and you can see the emission. The below of this voltage, the LED is off, and you can see the higher recombination rate of that. Okay, and also we can add emission rate with current. Let me add it. I can click right on it. On results in 1D, I can add global section. I just can copy the int of 1. Let me copy that, and I can do the integration of the position or geometry in the emission rate. Let me paste here, and the x-axis I can add the semiconductor terminals, semi I01, and I can add it as milliamp. And I also add the all voltages to see what the result will be. This is a total emission rate as a function of terminal current. This is a total emission rate. And for the internal quantum efficiency, let me check the 1D plot group, and I add the global. This is internal quantum efficiency. Just I can use this formula. Let me define it as IQE, internal quantum efficiency. I choose int of semi TRR spontaneous divided by let me semi dot I01 divided by E const I forgot this parenthesis. Okay, and X can be current. As we know, the quantum efficiency may be measured versus current, and I choose the plot, and I choose the all voltages. Okay, as you can see, we have the emission, the integral of emission rate divided by the current, that we call it as the internal quantum efficiency, IQE, and we can plot it as a terminal current, and we can talk about the efficiency. Okay, the simulation is done, and you can do the simulation for the, for example, LED perovskite LED. Let me check it for you. And also you can do the simulation for the, for example, silicone material, gallium nitride, and other material. Let me check the perovskite material, because the perovskite is up to date and researchers work on it. And excuse me for my internet. You can search the LED properties to see what the fabrication, what the type of LED is. And you can use a different structure for the simulation, but we need this LED just as a semiconductor material to understand the behavior. But you can add this other material, for example the epoxy lens, and also you can add the cathode anode as a 3D, but it adds the extra things to your model that complicate your computations. It takes longer to compute. It's better to use a simple model for your problem. Okay, I hope you enjoyed this video. Please subscribe to my channel, leave your comments, share my channel to your friends, and also like my videos, see all of my videos, and take care. Have a good time. Take care. Goodbye.